Let's learn about polar coordinates. So here's the basic definition of polar coordinates and some of the things that we'll find useful to discuss. So here you have what's called the polar axis there in orange. We're representing it as the plus x-axis there. The pole, which is the origin, and the distance to a point p r theta from the pole is this radial coordinate, okay? And the angle that you would wind up from the plus x-axis or the polar axis is the angular coordinate, theta. So this point here, r theta, has a distance from the pole r, and winding counterclockwise, so counterclockwise is the positive direction of winding, angle theta. Okay, and now you could wind even beyond 2 pi. So here, for example, if this here was theta, then going around once, well, that's 2 pi and then theta. And so you get theta plus 2 pi, which is effectively the same. It's not the exact same angular coordinate, but you land in the same position, okay? And so this is the point r theta plus 2 pi. Notice here in both of these examples that r is strictly positive, but we can even have negative r's. And how does that look? Well, here's the point pr theta, and negative r, so a negative radius, just essentially flips to the opposite direction the point, okay? So here's the distance r, angle theta. Negative r is in the opposite point relative to the pole, okay? And still with the angle theta, okay? You still have that angle theta over there, but so how do you find a point with a negative radius or a negative radial coordinate? You pretend that the radial coordinate's positive, so you go to r theta, and then you just flip it about the pole to get to the opposite point there, okay? And pr theta, well, that's the same as p negative r theta plus pi, okay? So we could do this in several ways. We could have, so if we go to the point p negative r theta, well, that's here, and then we add pi, and we end up at this point here. So that's what these equalities are showing you. We could also look at it as negative r theta minus pi, and what you're doing there is you're going, here's pr theta, you flip and you're p negative r theta, and then you wind back theta, okay? So you wind back at theta and you get to pr theta. So these are three representations of pr theta, and this is p negative r theta. P negative r theta could also be represented as, we could have used p r theta plus pi to represent that same point there. Okay, so several representations of the same exact point. So let's do an example. Let's consider this example right here. We want to graph these following polar coordinates with two alternative representations. So let's start with q1 5 pi over 4. Okay, 5 pi over 4 is basically pi plus pi over 4, or 45 degrees, so 180 plus 45 degrees. And so the standard way to do this is to just wind 5 pi over 4 counterclockwise, because it's positive, and you'll have a radial distance of 1, and so you end up at this point here. But we could have done this a different way. Notice that we could have also represented it as 1, and instead of winding counterclockwise, we could have winded clockwise, which is in the negative direction, and used negative 3 pi over 4. Alternatively, we could have went to q pi over 4. So here over here would be q 1 pi over 4. And notice that if we multiply the radius by -1, we get to flip it. And so here's another representation, q -1 pi over 4, or again winding clockwise -3 pi over 4, and the radial coordinate stays 1. What about r -17 pi over 4? So again, how do you find this point? My advice is to ignore that negative first and just wind around 7 pi over 4. And so, this extra angle here beyond the negative y-axis, pi over 4. Okay, so we get to 7 pi over 4. It's somewhere here. And then we find the distance 1 and then flip it to get to the point -17 pi over 4. And so here's our point. But what if we didn't want to use a negative radius? Well, we could just wind counterclockwise in the positive and get +3 pi over 4 for the angular coordinate, and just have a radius of +1. Okay? Well, we could flip both signs. We could wind down -pi over 4. Okay? Here would be the point 1 pi over 4, and then flip it. And so you'll get -1 pi over 4. That's yet another representation of the point R. Well, what about the point S, to -3 pi over 2? Again, how do you do that? Well, you need a radius of 2, and you're going to move down 3 pi over 2. Okay, so this point shows up is 3 pi over 2 is down there. Okay, so you're winding around, not +3 pi over 2. +3 pi over 2 would be there, but you go around 3 pi over 2 in the negative direction, and you have a radial distance of 2. And so here's our point S. Well, we could represent this as S plus pi over 2. Okay, so winding counterclockwise instead of clockwise. Or we could wind down minus pi over 2, so go clockwise pi over 2 and then flip the sign of the radius to end up in the point opposite relative to the pole. Okay, so several representations there. All right, well, we talked about polar coordinates, and how do we go to familiar territory? How do we relate that to the x and y points? Well, notice, okay, here's our point r theta, but it's also represented as xy, okay? And everyone knows how to plot a point with x and y. But notice something. This forms a right triangle. So if I have a side y there and a side x, and then I'll get a right triangle with my hypotenuse being the distance r, okay? And here goes my angular coordinate, and I could relate these two now. So x is equal to r cosine theta. Why? Because cosine theta is adjacent over the hypotenuse, r. Okay, the hypotenuse here is r. Sine theta is opposite, so opposite to theta, which is y, over the hypotenuse r, and that gives us this equation. So that's how you go from r theta to xy. Notice that on my left-hand side, they're red, they're in xy, and everything on my right-hand side is blue. Okay? So I'm using what I know, which is r and theta, to get what I don't know, which is x and y. What about the reverse? Using x, starting from xy and getting r theta. So on my left-hand side now are expressions of just r and theta, and on my right-hand side are expressions of x and y. And we get this because, again, this is a right triangle, so you have the Pythagorean identity there. R squared is equal to x squared plus y squared for the right triangle. And tan theta, well, that's just opposite over adjacent, and so you get y over x. Okay, and so that's how you convert back and forth between Cartesian and polar coordinates. All right, well, let's look at an example of conversions. So express the point P in Cartesian coordinates. All right, well, this is in polar coordinates, and so we just straightforward use the formula there, 2 cosine theta pi over 4, and you get negative root 2, and y is equal to r sine theta, and you get square root of 2 there when you plug the values 2 and 3 pi over 4 in this basic formula. What about when we're working in reverse? So we start with Cartesian coordinate x equals 1 and y equals negative 1. We're going to use these formulas, okay? And here we took the positive r, okay? And tan theta is equal to negative 1 gives us theta is equal to negative pi over 4 or 7 pi over 4. You notice that there is an ambiguity when working backwards, so going from Cartesian coordinates to polar coordinates, okay? When you take the square root of r, you could get positive or negative results, and you have to be careful when taking arctan, okay? You have to be careful with that because points, so if you put arctan of a point in the first quadrant, that looks similar to arctan for points in the third quadrant, okay, where both of them are negative. So if you imagine if y was negative y and x was negative x, well, the negatives will cancel. And so you got to peel your eyes and be mindful of what you're actually calculating when you do arctan. Likewise, you get an ambiguity between the second quadrant and the fourth quadrant. So you have to pay attention to which one is positive and negative there. Is it the y or is it the x? If it's the x, then you're in the second quadrant. The y is positive. If it's if the y is negative and the x is positive, well, you're in the fourth quadrant. So you do have to peel your eyes to know which angle you're dealing with. So let's look at basic curves in polar coordinates. Okay. Take a look at r equals a, where a is a constant. Let's just suppose it's 1. Then what are we saying when we say r equals 1? We're saying we want the set of points that satisfy the relation that the radial coordinate is 1. Well, anything on that circle will satisfy that condition. And so you get a circle. That's what r equals a, where a is a constant, represents. So it's a circle of radius a. What about theta being constant? Again, we're saying what are the points that satisfy theta being some fixed angle, say pi over 4. Well, then anything on this line will satisfy that. And so you'll get a line. That's what theta equals theta naught represents. But we could do something a little more wild, okay? So these would just be represented. So pay attention here that on what's traditionally the x-axis, or let's call it the horizontal axis, you have r and theta. You get a straight line of r versus theta, okay? Here, theta equals theta naught would have been just a constant, straight horizontal line, and r equals a would have been just a vertical line on axes that look like this. Well, r equals theta. Okay, how does that look when we want to consider that relation in the xy plane? Well, you're saying that r is theta, so right at theta equals 0, you get r equals 0, so you're right at that point. Then say you get to theta equals pi over 4. Well, here then would be the point r equals pi over 4 and theta equals pi over 4. Okay? Eventually you get up to pi over 2, pi over 2, and notice what's going on. You're just winding around. Okay? You're just winding around. And this is how, when we plot a polar curve in the xy plane, how it would look. Okay, But be mindful that r and theta here are on the horizontal and vertical axes respectively, and this is xy. Okay, so it's a very different beast, and they look very different. Okay, so let's look at an example with polar equations. So we got this polar equation. Again, we plug in values of theta and get an r value. And we want to know how that looks like in the Cartesian, in Cartesian coordinates. Well, here's some tricks to be able to convert such an equation into Cartesian coordinates. You start out with this equation, okay? Now, this isn't exactly amiable to Cartesian coordinates as it is, okay? I can sort of blindly plug in the, r is equal to square root of x squared plus y squared. You could do that here. You could take an arctan to get theta, and then plug it in here and in here. But it's not going to be very clear. Here's a better strategy. Multiply both sides by r. Okay. What does that buy you? Well, it buys you that you got an r squared on the left-hand side, so you don't have to deal with a radical, right? You don't have to deal with that square root. You just get that r squared is x squared plus y squared. And importantly, you have r cosine theta and r sine theta now. And these are easily converted to Cartesian coordinates, x and y, right? With the formulas that we have above. Okay, so just like that, we could write everything in terms of x and y. And we move everything to the left-hand side and complete the square to get this final relation after completing the square. And what does that look like? Well, it looks like a circle centered at 512, okay, with radius 13, because 13 squared is 169. Okay, so that's a way. Now, of course, you could have also plotted, just put in a different thetas and see what are you. That's a hard way. It's easier to just have done this. Generally, for circles in polar coordinates, here's how they're described more generally. For a circle centered at 0, 0, well, we saw that that's just r equals a if it has radius absolute value of a, okay? So you could just describe it by r equals a, okay? Even though this could also be negative, and you'll still get a radius you'll still get a circle of radius absolute value of a, okay? What about a circle of radius this, square root of a squared plus b squared at ab? Well, here's the general formula for that, okay? So it's a little restrictive on how, it's got to be centered at this and have that radius corresponding to where it's centered, but, we ran into this before, and so, okay, we'll add it to our formula list over there. We talked about plotting polar curves, and something that can make your life much easier when you're plotting polar curves is utilizing the symmetries, okay? So let's talk about symmetries and graphing in polar coordinates. So we have the symmetry about the polar axis, or the x-axis, that horizontal axis that we wind from, okay? And this symmetry occurs if whenever r minus theta is on the graph, r theta is on the graph, right? Or vice versa. So if r theta is on the graph, so is r minus theta. We also have symmetry about the y-axis, or symmetry about that vertical line at theta equals pi over 2. And this occurs if r theta is on the graph whenever r pi minus theta, which is equivalent to negative r, negative theta, is on the graph. And we have symmetry about the origin, right, which is what occurs when you flip about the x-axis and then the y-axis. Then that's characterized by r theta being on the graph whenever negative r theta or r theta plus pi, okay, these 2 points are equivalent, just like these 2 points are equivalent. So if this is on the graph, then this should be on the graph, and vice versa. A note here about these 2 points. Sometimes it's easier to prove the symmetry using negative r theta, and sometimes it's easier to prove the symmetry using r theta plus pi. Okay, it just depends on the sort of equation. It's the same exact thing with this, right? Sometimes it's easier to prove the symmetry with r pi minus theta, and sometimes it's easier to use negative r negative theta, depending on the equation. A remark here that any two symmetries implies the third. And let's take a look at a concrete example. So we want to graph this equation here, okay, by analyzing the symmetries. So let's look at the symmetries before we get started to know where we're going. So suppose r theta is on the graph. We want to show that negative r theta will also be on the graph. Why? Well, that's going to give us a symmetry about the y-axis. And how do we do that? Well, assume this. This is equivalent to negative 3. It's equivalent, right? Because sine of negative x is negative sine x. So you could pull out that minus sign and cancel it. So this is the same as that. Okay? Now move that negative to the other side, and look, you got a negative r there. You got a negative theta there. And they still respect the basic form, r3 sine 2 theta, right? So you have negative r and negative theta are also on the curve. They respect that general equation. Okay, and so you have symmetry about y-axis. You could have also worked backwards and just taken r to negative r and theta to negative theta. So start here and then show this. That also works. Okay. Something to note here. What if instead of negative r and negative theta we use pi minus theta? You could show that, but it's more complicated. And again, this comes from the fact that negative r's are this, taking theta to theta plus pi. So it gets a little confusing to show it that way. And again, which point you use really depends on the equation that you're given. Here you have just an r on the left-hand side and a sign there on the right-hand side. It's easy to show with negative r, negative theta, the symmetry about y. Well, what about symmetry about the origin? Okay. We could add a 2 pi. And again, what are we aiming for? We're going to aim for showing this. All right. And we could add 2 pi. So sine x plus 2 pi is just sine x. You could feel free to always add as many multiples of 2 pi's as you want. And that affords us factoring out that 2. And so we have a theta plus pi in the argument of the general form of the equation, and we have the r. So this can only be true whenever this is true. And so what does that tell us? That tells us that r theta plus pi is also on the graph whenever r theta is on the graph, and vice versa. So you have symmetry about the origin. Again, we could have aimed for showing this using r theta. So we would take that r here and make it a negative r equal to 3 sine 2 theta. But it's not as easy to show because of that flipping about the pole issue. In symmetry about y, about the y-axis and origin, so two of them, imply symmetry about x. Okay, so we showed 2, it implies the third. If we want to show symmetry about the x directly, again, it's not so clear because you'll have this negative r, you'll have r negative theta, you'll get a minus sign out there. And it turns out that the point is on the curve, but because of that minus sign, it's less clear. Okay? So always shoot for what's simpler. All right, and so since we know this has all 3 symmetries, we only have to plot the first quadrant. Plotting the first quadrant, then we could flip it around about the y-axis. We know we have symmetry about y, and we know we have symmetry about x, so we could flip it around, and you'll get the full curve. But what if we just plotted it directly? Let's do that. Notice here on the left hand side, again, this is r and theta, not x and y. Okay, x and y is on the right. That's r and theta. So what are these points? Okay, well, as we increase theta, we increase r. We hit a peak. Here's the peak. That's the maximum sort of r. That length there from the origin to that point there is 3. And then as we wind to pi over 2, we hit 0 again. Okay, and so here we are at the pole. But what about this guy here? This is a little tricky because r is negative. Okay, r is negative there, so you're going to be a tiny bit careful. You're increasing beyond pi over 2, and you are getting a negative r. And so, it's not that leaf in the second quadrant. It's actually the leaf in the fourth, okay, because of that negative r. And you hit back 0 again at pi. Okay. Well, then beyond pi, we'll get positive r. So how are we going to plot that? That looks like this. Okay. And then finally, we're in the negative r territory again, and you end up getting this. And right back down to pi as you go towards 2 pi. Okay, and so that's how these, that r theta maps onto the xy. And I'll leave you with just some kind of useful properties here. That sine of pi minus theta is equal to sine theta. And so if you see just the sine theta, you might shoot for showing y symmetry, symmetry about the y-axis with that point. A useful property there, cosine negative theta is cosine theta. Theta plus pi, tan theta plus pi is tan theta. Sine negative theta is equal to negative sine theta. And, that's just some useful formulas there for showing symmetry.